Vous poursuivez.
Goodbye, thank you.
Québec Kilo, je reviens à l'ouest.
Bonjour à tous.
Hello there. The aircraft I'm standing in front of is a RJ-85 of our national airline. Every winter it operates charter flights to bring tourists here to Sion, mainly from the UK. But landings and takeoffs at Sion can often pose quite a challenge given the airport's location in the Rhone Valley with mountains all around. And despite their avionics used for flying on instrument flight rules, some of these charter services have to be cancelled when visibility gets bad. This is one of the reasons Sion has been selected by Europe's leading aeronautical specialists to trial the GNSS-EGNOS. So what exactly does GNSS-EGNOS involve? Let's take a closer look.
Explication en images.
These passengers probably don't realise it, but they're part of a revolution in satellite navigation technology. For some years now, the Global Positioning System, or GPS, has enabled aircraft to pinpoint their location on the world's airways. These satellite applications are still fairly limited. The systems cannot yet be used to enable takeoffs and landings, but they could be soon. These scientists have gathered here from all over Europe to push this satellite technology further. They have been handpicked from the continent's air traffic management organizations and its finest universities to develop a new system called GNSS-EGNOS under the overall Galileo project.
EGNOS will allow us to enhance the precision and integrity of GPS, and that will enable us to fly approaches and other operations that we can't currently perform with GPS.
There are some 50 satellites orbiting 24,000 kilometers above the Earth. Shown in green are the GPS satellites of the United States, and shown in red are their Russian counterparts of the GLONASS system. In order to navigate by GPS or GLONASS, an aircraft needs to have 4 satellites at its disposal at all times to fix its position. EGNOS works on the same principle. But under EGNOS, the data provided by the satellite are also received by a station on the ground called RIMS and are then sent on from here to a processing centre. The whole package is then transmitted to the aircraft via a geostationary satellite.
The user will receive their data both from GPS and from EGNOS. This will enable them to improve their precision and, above all, the integrity of their navigation system.
We're now aboard a Dornier 128, but it's one that's been transformed into a flying laboratory to conduct research all over Europe for the University of Braunschweig in Germany. Today the aircraft, which is packed with computers and electronics, is simulating approaches and departures while guiding itself solely by satellite, and it's recording the parameters of its position in real time throughout the flight.
The information we gather is recorded every second, so we're talking about a vast mass of data here. In fact, if we recorded like this for 24 hours, we'd accumulate about 120 megabytes of data. The first tests we're currently conducting with the prototype system have given us a horizontal precision of within about 2 meters and a vertical precision of within about 3 meters.
The investigators have placed these satellite antennas on the ground at various locations around Sion Airport. They are used to determine the exact position of the aircraft at every point in the process.
Needless to say, you wouldn't ordinarily have all these antennas here, but we're still in the prototype testing phase, so we have a lot of parameters to measure right now, and that's what all the antennas are there to do.
The new system also needs to ensure that contact is constantly maintained with the satellites above. In this respect, it's logical that Sion has been chosen for these trials.
The problem is that GPS tends to be used in relatively open sky. But here at Sion we have mountains to the left and the right. These can interfere with the signals or weaken them. Our tests are designed to measure the impact this can have on the quality of the data reaching the aircraft, and the impact this might have in turn on the aircraft's navigation.
With an instrument flight rules or IFR landing, the aircraft is guided by radio beams indicating the heading and the glide slope it needs to follow. This display tells the aircraft it is correctly tracking towards the landing runway, but is a little below the glide path required. This instrument, the distance measuring equipment or DME, indicates the distance remaining in nautical miles to the radio beacon. The beams emitted by these landing guidance systems are always straight, however at Sion, the Rhone Valley is curved.
You have to descend at a very steep angle, about 6 degrees, with the current glide slope. And this is something that today's aircraft are not generally designed to do. Here, above the town of Sierre, at 8,000 feet, and 13.1 nautical miles from touchdown is the decision point for any aircraft where the flight crew has not been trained for landing in Sion.
At an airport like Geneva, the localizer beam is lined up along the runway's centre line. Here at Sion, because of the shape of the valley, the localizer beam is offset from the runway alignment, so the pilot has to make a turn to the right at the last moment to land on the runway. But this turn and the landing have to be performed visually. So although the airport has an instrument landing system, landings cannot be performed at Sion when the visibility is poor.
A pilot who is licensed to perform IFR landings at Sion will have a decision height which is different from that of a pilot not licensed for such landings. This means that the latter will have to decide earlier if they can land at Sion or not.
The only solution to this is to find a means of guiding the aircraft all the way to the runway threshold by flying a curved approach. Eurocontrol, the umbrella organisation for Europe's air traffic control, has already shown that this can be done. Tests of the GNSS-EGNOS system in Nice allowed pilots to avoid approaching the airport directly over the Cap d'Antibes and thereby reduce the noise to which local residents were exposed.
The EGNOS system can be used to improve special situations like at Nice and Sion. So it's a real success for the civil aviation world, and people are delighted to see what can be achieved using the satellite-based EGNOS approaches.
Landing at an airport is one thing, but you have to take off from it too. We're now aboard Swiss Flight 2632, which is bound for London Heathrow. In normal conditions, the aircraft could simply take off and climb straight ahead along the Rhone Valley to leave this mountain environment. But today, our aircraft is carrying 88 passengers. It's too heavy to do that. So the crew has to adopt a standard departure procedure.
Under this standard departure, the aircraft will climb and accelerate to a waypoint known as Grana, located to the east of Sierre. It will then turn from this point to climb along a specified track to a safe altitude well above the surrounding terrain.
To reach Grana, the aircraft will need to fly up the Rhone Valley, climbing to an altitude of 6,000 feet or around 2,000 meters. At this stage in the flight, the procedure calls for the pilots to have constant visual contact with the ground, and this can sometimes cause problems during winter when charter services are operated.
If the cloud base is too low, the aircraft will have to fly empty to Geneva and pick up its passengers there, and that, of course, is very inefficient.
Pilots flying out of Sion must always contend with the mountainsides nearby. GNSS-EGNOS would be the first work tool ever that could simplify the existing procedures. This is also, incidentally, the first time that the GNSS-EGNOS project has tackled takeoff problems too.
What we are trying to evaluate with these trials is routing over Martigny, turning towards Lake Geneva, which will give us the option of either returning overhead for a second approach or leaving for Geneva for an ILS approach there.
The first data has now been collected and the analysis work can begin. This analysis will be conducted in close collaboration with everyone working on the project.
We'll be evaluating the data at SkyGuide. The Lausanne Federal Institute of Technology also has an interest at the in-service training level, and one of its diploma students will be evaluating the data. Eurocontrol is involved too. They're also sorting through the data to ascertain its quality and integrity, so there are three parties involved in the assessment.